All right, let's jump straight into this explainer. Today, we are tackling the geometry of circles and putting together your absolute ultimate study guide for the JEE exam. If you've been searching for a breakdown that perfectly highlights the really essential circle equations and properties without the fluff, well, you are exactly where you need to be.
So take a look at our master schematic. Think of this as your quest map. We're going to map out the Cartesian plane like it's a physical landscape, and we're going to master the circles so you can finally conquer your final boss, the JEE. You know, too often, we just get completely bogged down in dense, messy algebra, and we actually lose sight of the shapes we're manipulating. By using this schematic, we are intentionally tossing out rote memorization. Instead, we're building deep, visual intuition. Every single equation we're about to discuss, it's simply a tool to help you navigate this map.
Okay, let's establish our foundation with a really simple geometric analogy. Think of the standard form, x squared plus y squared equals r squared, kind of like a dog tied exactly to a post at the origin, 0, 0. The radius r is the leash. It is perfectly symmetric, it's simple, it's our home base. But we don't always stay at home, right? The central form is essentially a joystick. By dialing in those new variables, h and k, you physically slide your circle's center across the Cartesian landscape to a completely new coordinate, all without ever changing the length of your leash.
Now, what's really crucial here is realizing that when we crack open and expand that central form, boom, we get the general form. That's your x squared plus y squared plus 2gx plus 2fy plus c equals 0. Instead of h and k, the variables g, f, and c act like these complex dials on a dashboard. Turning them simultaneously shifts your circle's anchor point to -g, -f, while inflating or deflating its overall size. Oh, and we also have the diametric form, which is super elegant. It anchors a circle using just the two extreme opposite ends of its diameter.
Wait, hold up, because here is a massive trap you absolutely need to avoid. Just because you see an algebraic equation that looks like a circle doesn't mean it actually is one. Before you just assume it's a circle, you've got to run a quick diagnostic check. Simply calculate g squared plus f squared minus c. If that number is greater than 0, awesome, you have a real, breathing circle. If it equals exactly 0, your circle has completely collapsed into a single microscopic point. And if it's less than 0, well, it's an imaginary circle. It literally does not exist in our geometric reality. No way around it.
All right, moving right along to the next section, lines, chords, and tangents.
So, as our circle is just journeying through the plane, it's inevitably going to bump into straight lines in one of 3 distinct ways. This basically illustrates the tension between a line's perpendicular distance from the center, let's just call that d, and the circle's radius, r. It's a really simple comparison. If d is less than r, the line violently cuts right through our circle, creating 2 intersection points and forming what we call a chord, or a secant line. If d is greater than r, the line just completely misses. But the real magic happens right in the middle, when d exactly equals r. The line perfectly grazes the boundary at exactly one single point. That right there is your tangent.
Let's zoom in on that grazing tangent for a second. How do we actually find its equation? Well, there are 2 main pathways. If you're already standing directly on the circle's boundary at a very specific coordinate, you just use the point form. Easy. But if you only know the angle or the trajectory the line needs to take, you use the slope form by plugging in your external slope m. And hey, notice that plus or minus symbol sitting in the slope formula? That mathematically guarantees you're going to find both of the parallel tangents that can exist for any given slope. Pretty neat, right?
Now, to navigate this landscape fast, which you need to do for the JEE, you need a secret weapon. And S1 is exactly that. It's essentially an algebraic substitution that instantly reveals your coordinates on the map. You just take your circle's equation, bring everything over to one side so it equals 0, and call that whole chunk S. Then you literally just drop your specific points x and y coordinates right into the equation. The number that spits out, that's your S1.
And calculating S1 is like an instant reality check. If S1 is a negative number, meaning less than 0, you are trapped inside the circle. If S1 equals exactly 0, you are standing perfectly balanced on the boundary edge itself. And if S1 is positive, you are completely safe hanging out on the outside. But wait, it gets better. If you are on the outside, taking the square root of S1 instantly gives you the exact length of the tangent line drawn from your location straight to the circle. It's an absolutely phenomenal shortcut.
Okay, so we've got the single circle dialed in. Its center, its radius, the lines hitting it, but we've got to escalate our quest now. The true test is asking, what actually happens when complex factions of multiple circles collide and interact with each other?
This diagnostic matrix right here is your cheat code. It's totally fascinating how just comparing the distance between two centers, let's call it D, to the sum or difference of their radii determines absolutely everything. If the centers are super far apart, where D is greater than the two radii combined, the circles are totally disconnected, meaning they can share 4 common tangents. But as you push those circles closer together, D decreases. They touch externally at 3 tangents, then they intersect to share 2, touch internally for just 1, and eventually one completely swallows the other whole, dropping to 0 common tangents. Visualizing how these variables change makes the complicated algebra feel completely intuitive.
Next up, Section 3, Dodging JEE Traps, the boss battle.
To actually win this battle, you need high-yield accelerators. We're talking rapid-fire tactics that completely bypass pages of dense algebra, using elegant geometric shortcuts. Take parametric power, for instance, converting messy x and y coordinates into a single, clean angle theta. Or radical speed. If you need the common chord between two intersecting circles, please don't do complex substitutions. Just subtract their equations. S sub 1 minus S sub 2 equals 0 instantly hands you that straight line of intersection. And hey, if a chord subtends a 90-degree angle at the center, don't calculate the distance. Just know the length is instantly r times the square root of 2.
But, and this is absolutely crucial, you have to be aware of the critical system traps. Listen closely, because these are the exact blind spots examiners exploit to make you fail when you rely blindly on algebra. Look at the t equals 0 assumption. Sure, the formula t equals 0 generates a tangent line perfectly, but only if the point you're using is actually sitting on the circle. If the point is hovering somewhere outside, t equals 0 gives you a chord of contact instead. If the point is inside, it gives a random chord, not a tangent. You absolutely must verify S sub 1 first. And watch out for the general form fakeout. If an equation starts with 3x squared plus 3y squared, you must divide the entire equation by 3. Normalize those coefficients to 1 before you even think about extracting the center or the radius.
Which brings us to a fundamental philosophy for tackling advanced math. Always remember our primary mantra for this quest. Calculating blindly is a trap. Visualizing the geometry is the actual shortcut. When you are sitting in that exam hall, draw it out. If a triangle inscribed in a semicircle has an angle on the boundary, you don't need any messy distance formulas to know it's exactly 90 degrees. You can just see it. Let the geometry guide the algebra, not the other way around.
I'm going to leave you with this final, honestly beautiful thought to explore. When you take the equations of two base circles, S sub 1 and S sub 2, and you blend them together with a variable dial called lambda, you don't just get one new circle. You spawn an entire, infinite coaxial system of interconnected circles all passing through the exact same intersection points. How crazy is it that tweaking a single variable can spawn an entire universe of shapes? Ponder that visual the next time you look at a simple algebraic formula. Thanks for mapping out the Cartesian plane with me on this explainer today. Keep visualizing, and you're going to master this landscape in no time.